What if I told you that a tiny 3 billion parameter neural network just completely outsmarted AI monoliths 200 times its size? Like, we are talking graduate level mathematics and complex algorithmic coding. Today on AI Paperslock, we're doing a deep dive into a really landmark release. It's called VibeThinker-3B, exploring the frontier of verifiable reasoning in small language models. And it is hot off the presses from researchers at Sina Weibo Inc.
Yeah, and if you are a machine learning engineer or, an AI researcher or honestly just anyone tracking current scaling laws, this is the paper that kind of breaks the established trend.
It really does. I mean, we're talking about a strictly 3B parameter model hitting absolute frontier level reasoning scores. It got a 94.3 on the highly rigorous AME 2026 math benchmark, and that actually scales up to a 97.1 with test time compute.
Right, which is just wild for a model that size.
Exactly. And on coding, we're looking at an 80.2 pass at 1 on Live Codebench version 6. Just to put that in perspective for you, this tiny model, which you could comfortably run locally on a decent laptop, is matching or outright beating the 671 billion parameter DeepSeek v3.2, the 744 billion GLM5, and Gemini 3 Pro.
The benchmark numbers are undeniably staggering, yeah. But I think the theoretical framework driving those numbers is really what makes this paper so critical for the field right now.
Okay, let's get into that framework then. What's the core idea?
Well, the Sina Weibo researchers introduced what they call the parametric compression coverage hypothesis. The central claim here is that verifiable reasoning, so things structurally constrained by rigid rules like logic, math, code, can actually be heavily compressed into a dense 3 billion parameter core.
So you don't need a massive brain just to do pure logic.
Exactly. It's only the open domain encyclopedic knowledge, the messy, unconstrained facts of the universe that actually demands massive parameter scales to memorize. We're seeing this hard architectural decoupling of logic from knowledge.
That is huge. So let's dissect exactly how they pulled this off. Our mission today is to tear down their spectrum to signal post-training pipeline. We really need to understand the mechanics of how they squeeze this massive reasoning capability into such a tiny footprint, starting basically from the ground up with initialization.
Right, because you can't use reinforcement learning to amplify a behavior if the model doesn't even know how to generate that behavior in the first place.
Right, exactly. So building that foundational behavior, that happens in the supervised fine-tuning, or SFT, phase.
Yeah. And the goal here is to establish a diverse spectrum of valid logical paths before the REL, the reinforcement learning, even begins.
Yeah.
They initialize the training with the Qwen 2.5 Coder 3B base model, but the real differentiation is in their data quality pipeline.
And the filtering is incredibly aggressive.
Oh, heavily aggressive. They deploy n-gram deduplication specifically to strip out templated degeneration, because small models often fall into this trap of memorizing repetitive loops and boilerplate coding patterns rather than actually, thinking through the problem.
Right. N-gram deduplication forces the data set to remain varied. And then they deploy an LLM-based judge, right, to basically comb through the data and filter out any queries that contain fundamentally flawed logic or impossible conditions.
Yeah, exactly. And finally, they enforce strict trace correctness. If a training example includes code, that code has to execute in an isolated sandbox without throwing a single error.
Not a single error.
Not one. And if it's a math derivation, every single step must perfectly verify all the way to the final answer.
So we basically have a baseline of absolute, undeniable truth, and they structure this data into a highly deliberate two-stage curriculum. I want to spend a second on stage 1, which focuses on broad coverage. The paper mentions they use sequence packing to efficiently train across math, code, STEM, and general chat simultaneously.
Yeah, sequence packing.
Walk me through the actual mechanics of that. Why is sequence packing necessary here rather than just training on those domains sequentially?
Well, sequence packing essentially crams multiple, diverse examples from completely different domains into a single, contiguous training sequence. So it fills the model's context window completely.
Okay, so they're mixing it all together.
Right. When you put a Python script, a calculus proof, and a multi-turn chat log into the exact same batch, the model's self-attention heads are forced to process them concurrently. By mixing these formats, it basically prevents the attention mechanism from overfitting to the specific syntax of one single domain.
Ah, I see. So the model is forced to look deeper and recognize the underlying logical structures and causal relationships that are shared across all of those domains.
Exactly. It builds a generalized reasoning foundation rather than just a memorized syntax lookup table.
That makes a lot of sense. It's like learning the universal grammar of logic before you specialize in a specific language.
Yeah, that's a great way to look at it.
Okay, so then we get to stage 2, which is hard reasoning. They basically throw out any reasoning trace under 5,000 tokens, and they also filter the queries through their older 1.5B model, and if that smaller model solves the problem more than 25% of the time, so an error rate below 0.7 dev, they discard it.
They just toss it out. The problem is deemed too easy.
It reminds me of the academic journey, you know. Stage 1 is like reading the entire university library to understand the baseline of human knowledge. And then stage 2 is being locked in a room where the only things you're allowed to interact with are postdoctoral dissertations on theoretical physics.
Yeah, that's literally what they're doing to the model.
But I have a mechanical problem with this approach. Like, if you are aggressively filtering for only the longest, hardest, and most strictly correct traces, aren't you completely collapsing the model's creativity?
How do you mean?
Well, you are forcing it into a highly deterministic, narrow way of thinking, which seems like the exact opposite of what you want right before an RL phase, right?
Right. That's a super valid point. And the Sina Weibo team actually anticipated that exact trap. Because you're right. If the model only knows one hyper-specific way to solve a hard problem, the reinforcement learning algorithm has no alternative paths to explore. It just gets stuck in a local minimum.
Right. So how do they fix it?
They solve this using a technique called diversity exploring distillation. Normally, during SFT, engineers track the validation loss over time and they just save the single checkpoint that scores the lowest, because a low loss implies the model is fitting the training data perfectly.
Right, which usually leads to mode collapse. The model just memorizes the most frequent solution path and entirely ignores alternative creative ways to solve a problem.
Precisely why they abandoned that standard practice. Instead of relying on validation loss, the researchers evaluated intermediate training checkpoints using PASIC-K on domain-specific probing sets.
Okay, wait, break down PASIC-K for us real quick.
Sure, so in PASIC-K, you basically generate K different responses to the exact same prompt. The researchers were actively measuring how many different valid ways the model could solve the same problem across those K generations.
Oh, wow. So they're optimizing for variety.
Exactly. They identified the specific training checkpoints that produce the most diverse array of valid solutions across different domains. And then they merged those checkpoints together at the parameter level.
That is brilliant. So the resulting unified SFT model maintains a massive solution spectrum. The exploration space remains incredibly wide open for the reinforcement learning phase that comes next.
That's it, exactly. They built a really wide spectrum of correct paths. But here's the catch. A 3 billion parameter model doesn't have the compute capacity to wander around guessing at runtime.
Right, it's too small for that.
Yeah, it needs strong signals to know which of those paths are the most reliable under pressure. And this brings in their multi-domain reinforcement learning phase. The core engine driving this is Maxent-Guided Policy Optimization, or MGPO.
Okay, MGPO. What makes this different from standard RL?
So MGPO is engineered to target the model's capability boundary with extreme mathematical precision. In standard reinforcement learning, you honestly often waste immense amounts of compute updating the policy on prompts the model already solves perfectly.
Or penalizing it for prompts that are completely beyond its current capacity, right?
Right. So what MGPO does is it calculates the empirical group accuracy for every single prompt by sampling a batch of responses. Then it applies a mathematical weight that heavily prioritizes the prompts where the correctness deviates the least from 0.5.
A 0.5 success rate. Maximum entropy.
Exactly.
Let me synthesize that. It's essentially looking at a teacher managing a classroom of students. If the class gets a specific type of math problem right 100% of the time, the teacher skips it. There is no learning left to do there.
Yep.
And if they get a problem wrong 100% of the time, the teacher also skips it because the students clearly lack the foundational steps to even begin grasping the concept.
That is a spot-on analogy.
So the algorithm is hunting exclusively for the coin toss problems. It wants the problems the model gets right exactly half the time because those sit right on the frontier of the model's understanding, meaning that is where the gradient signal will be the absolute strongest.
Exactly. And focusing on that maximum entropy boundary produces these highly stable, highly efficient policy gradients. It prevents the model from over-optimizing on easy tokens and stops it from degenerating into noise when faced with impossible problems.
That's super elegant. But While applying this RL phase, didn't the researchers have to make a massive pivot regarding the context window?
Oh yeah, a complete 180.
Yeah, because they completely reversed the strategy they published in their previous VibeThinker 1.5b paper. I caught that detail. In the 1.5b paper, they used progressive context expansion. They started the RL phase with a very short context window, let the model learn the basics, and then slowly increase the window size to save on expensive compute costs.
Which is standard practice normally.
Right. But for this new 3B model, they threw that playbook out entirely. They just blasted the model with a single 64K context window from step one. Why the sudden reversal?
It traces directly back to the quality of the stage 2 SFT data we just discussed. Remember, they filtered out everything under 5,000 tokens.
Right.
So the model's established baseline behavior is deep, complete, long horizon logical derivation. When the researchers tried applying a heavily truncated context window early in the RL phase, it artificially cut off those long thought processes.
Oh, I see.
Yeah, the model was forced to output a final answer before it had finished reasoning, literally just to fit within the artificial window limit. It accidentally trained the policy to favor incomplete shallow logic.
Wow, that is a brutal failure mode. You spend all this compute teaching it to think deeply, and then the truncation literally forces it to take shortcuts just to survive the training environment.
It was bad. And the degradation was incredibly sticky too. Even when they expanded the context window later in the training run, the model had already internalized those bad shortcut habits.
Oh man, so it was permanent.
Yeah, it was almost impossible to recover that deep reasoning capability once it was lost. So to preserve those complex reasoning trajectories, they just had to absorb the massive compute cost and give it the full 64K window right from the start.
Which creates a massive secondary problem because, okay, if we are blasting this model with a 64K context window and we are heavily rewarding it for long, unbroken chains of logic.
You know where this is going.
Yeah, don't we run the risk of it writing a rambling 20-page novel just to solve a basic algebra equation? I mean, inference costs scale with every single token generated. How do we fix the verbosity and make the model efficient without breaking the underlying logic?
This is the exact purpose of their long to short math RL phase. It's a deliberate, highly calculated transition from optimizing for pure accuracy to optimizing for token efficiency.
Okay, so how do they do that without wrecking the model?
Doing this without destabilizing an already fragile reasoning model requires a very careful mathematical balancing act. Once the model's accuracy was firmly established, the team introduced a zero-sum reward shift.
Wait, break down the mechanics of a zero-sum reward shift for us. How do you mathematically punish length without the model thinking you are punishing the correct answer itself?
Good question. So in reinforcement learning, the model relies on a group-level reward baseline to understand if a specific action was better or worse than average. If you blindly penalize all long answers, you drag down the entire baseline and the training can completely collapse.
Because the model just stops generating answers at all to avoid the penalty.
Exactly. It's safer to say nothing. So the long to short phase only redistributes rewards within the subset of correct trajectories. Let's say you sample 10 responses to a prompt. 5 are right, 5 are wrong.
Okay, tracking.
The wrong ones get standard negative rewards. For the 5 right ones, the algorithm calculates their token lengths. It boosts the positive reward for the shorter, more concise correct answers and applies a penalty to the longer, more verbose correct answers.
Ah. So the sum of the adjustments across those 5 correct answers is exactly 0.
Exactly. The overall mean reward for the group doesn't drop.
Meaning the model's understanding of what constitutes correctness stays perfectly intact. It just subtly reshapes its internal preference toward concise logic.
Yep, it's an incredibly elegant way to compress the thought process. But remember, this is a multi-domain model. They run this RL pipeline sequentially so. First math RL, then code RL, then STEM RL.
And training domains sequentially introduces the very real risk of catastrophic forgetting.
Huge risk, yeah. As the neural weights update to favor coding logic, they start overwriting the mathematical foundations learned in the previous step.
Which makes sense, because the neural network only has 3 billion parameters. It cannot compartmentalize easily. And you obviously don't want it forgetting calculus just because it spent the last epoch mastering Python.
No, you don't. So, to solve this, they implemented an offline self-distillation phase to unify the capabilities.
Yeah.
They took the highest quality reasoning trajectories generated during the separate RL stages and basically used them as a teacher to distill knowledge back into a unified student model.
But they didn't just dump all the correct answers into the student, right?
No. They applied a really crucial filter called learning potential filtering. They scored the verified teacher trajectories using the length-normalized negative log likelihood of the student model.
Okay, hold on. Let me make sure I am translating that metric correctly for our engineers listening.
Go for it.
In a language model, log likelihood is essentially the probability distribution of the model guessing the next token. So a highly negative log likelihood means the student model finds that specific sequence of teacher tokens highly surprising, like it did not expect that answer.
Yep.
Which implies the student does not understand the underlying logic yet. So the algorithm is actively hunting for the verified SFT solutions that the student model is currently the most confused by.
That's a perfect way to explain it. High surprise equals high distillation value. The trace contains a reasoning pattern the student hasn't mastered. Now, they did implement a ceiling to filter out extreme outliers, so traces that were so surprising they were likely formatting errors or corrupted noise.
Right. You don't want it learning from actual garbage.
Exactly. But prioritizing the middle to high surprise scores allowed the model to rapidly absorb complex cross-domain reasoning skills without wasting time relearning things it already knew.
Awesome. And just to round out the training pipeline, they run a quick instruct RL phase at the very end, don't they?
Yeah, they do. Because after all this intense mathematical and algorithmic reinforcement, you still need a model that actually listens to basic user formatting commands.
Right, like they implement rubric-based rewards and strict constraint checking so it obeys instructions regarding formatting, keyword limits, and JSON structuring.
Because a world-class reasoning engine is functionally useless in an enterprise environment if you cannot trust its output formatting to interact reliably with an API or, a larger software system.
Absolutely. Okay, so the pipeline is complete. We've gone from diverse SFT through maximum entropy RL, fixed the verbosity with long too short, and unified it all with self-distillation. Let's look at how it actually performs at inference, because there is one final test time trick they use to push the scores into the stratosphere. Claim level reliability assessment, or CLR.
CLR is a fascinating approach to test time scaling. Traditionally, if you want to scale compute at test time to improve accuracy, you generate many full reasoning phrases, and then you run a separate verifier model over the whole verbose output to pick the best one.
Which is massively token-intensive and slow.
Super slow. CLR takes a much more surgical route. The model generates 32 candidate trajectories, but instead of verifying the massive block of text, it uses its own logic to extract exactly 5 critical claims, or logical anchors, per trace.
Okay, think of it like pulling out the 5 load-bearing steps of a mathematical proof.
Yes, exactly. The model then acts as its own self-verifier, attempting to validate or falsify just those 5 isolated claims.
So it's isolating the most critical junctions of the problem and double-checking its work only at those specific points rather than, rereading the entire essay.
Yeah. And these binary verdicts on the 5 claims map into a nonlinear trajectory score. If even one intermediate claim is flagged as flawed, the entire trace is heavily penalized and discarded. It drastically reduces the token consumption required for verification while significantly boosting the pass at 1 performance.
Let's look at what that CLR boost actually achieves, because grouping these numbers together paints a wild picture of the current state of AI. With CLR active, VibeThinker-3B hits a 97.1 on the AMY 2026 math benchmark.
Unbelievable.
And on the Brumo 2025 Math Olympiad benchmark, it hits 99.2. It is literally acing graduate-level mathematics at a fraction of the compute costs of the industry leaders. We are talking about matching the 744 billion parameter GLM5 and Claude Opus 4.5.
It's just a paradigm shift.
It is. And on the coding side, hitting an 80.2 on LiveCodeBench v6 is great. But the out-of-distribution tests are what really solidify this as a breakthrough for me.
Well, yeah, evaluating on out-of-distribution data is the only empirical way to prove a model hasn't just memorized the training set. They tested this model on entirely unseen LeetCode weekly and bi-weekly algorithmic contests from April and May of 2026.
Meaning there is zero possibility of benchmark contamination. The model had never seen these specific problems during its training run.
Not at all. And on those completely novel algorithmic challenges, the 3B model achieved a 96.1% acceptance rate on its first attempt Python submissions.
That is insane.
It is running neck and neck with GPT 5.2 and Gemini 3 Flash on pure logic tasks. And regarding that InstructRL phase we mentioned earlier, it scored a 93.4 on the IHEVL benchmark, which basically proves it can flawlessly follow complex formatting rules while doing this heavy computational lifting.
Which brings us to the underlying why of this entire paper. We have undeniable proof that a 3B model can match a 700B monolith on complex logical derivation. Why is this physically possible within the architecture of neural networks? Let's go back to the parametric compression coverage hypothesis you introduced at the start.
Right. So the researchers are arguing for a fundamental architectural decoupling of two cognitive tasks, logic and knowledge. Verifiable tasks like algorithmic search, constraint satisfaction, correcting mathematical errors, they exist within structurally constrained spaces.
Right. The syntax of Python is finite. The rules of calculus are rigid and unbending.
Exactly. Because the rules do not change, these capabilities are what the researchers call parameter dense. The core logic patterns can be heavily compressed into a very small, highly reusable reasoning core. You do not need a trillion parameters to understand that 2 plus 2 is 4, or how a for loop operates across different variables.
But there is a glaring caveat in the data that proves the other half of their hypothesis. If we look at the GPQA Diamond benchmark, which tests graduate-level science trivia across chemistry, biology, and physics, VibeThinker-3B only scored a 72.9.
Yeah, that's a big drop.
It still trails the massive flagship models by a massive margin on that specific test.
And that performance gap perfectly validates their theory. Knowing the atomic weight of a rare isotope or the cellular pathway of a specific protein isn't a logic problem. It is a memorization problem.
Right.
Open domain facts, domain-specific concepts, and semantic associations across vast historical literature are parameter expansive. They require actual parameter volume, literal neural storage capacity, to capture the broad coverage of the universe's long-tail data. You cannot mathematically compress the capital of every country in the world the way you can compress a sorting algorithm.
So we've essentially proven that knowing things and thinking through things are two fundamentally different hardware problems. Small models can host world-class reasoning engines, even if they physically lack the hard drive space to store the entire encyclopedia of human knowledge. The development of compact models is no longer just a cost-saving measure for edge devices. It is a completely different, complementary architectural path.
The industry assumption has long been that scaling up parameter count was the only way to unlock deeper reasoning. This paper demonstrates that reasoning is actually an emergent property of data quality, curriculum structuring, and reinforcement strategy, not just raw parameter volume.
Which leaves us with a massive, forward-looking question to end on. If reasoning can be this densely compressed into just 3 billion parameters, will the ultimate frontier of AI architecture abandon these massive do-everything monoliths? Are we moving toward a future where a tiny, ultra-efficient 3B reasoning brain acts as the central orchestrator, and it simply queries a massive non-reasoning knowledge database model only when it needs raw facts? Think about what that means for inference costs, latency, and how we deploy AI in the real world. We are going to leave you with that orchestration future to ponder.